In 1945, at the peak of American industrial might, the Indianapolis assembly lines of the Allison Engine Company were churning out thousands of liquid-cooled V-12s. Then the sky abruptly changed. General Motors had transformed a precision machine shop into an empire that built over 70,000 Allison V-1710 engines. They had powered the P-38 Lightning and the P-40 Warhawk. But the sudden arrival of the gas turbine, the jet engine, turned the pinnacle of American piston aviation into instant military surplus. Thousands of 1,500 horsepower engineering masterpieces, once worth tens of thousands of dollars, were suddenly boxed up in wooden crates and sold to the public for as little as $50. The engine was a mechanical triumph, yet it became structurally obsolete before the factory even stopped the line. But the real story of the Allison V12 is not only the story of how an aviation empire lost the sky, it is the story of how America built a machine so powerful it refused to die, finding a second life in a roaring post-war underground of unlimited hydroplanes and rural tractor pulls. Long after the industry had moved on, every week we tell the stories of American engines, factories, machines, and industrial names that once taught the country what power sounded like, and what happened when the market moved on. Subscribe if that history matters to you. The story begins not with nostalgia, but with a specific place in Indianapolis in 1928. Indianapolis, 1928. The American engine landscape was largely defined by heavy iron, farm tractors, and the steady, low RPM rhythm of industrial power. But on the grounds of the Indianapolis Motor Speedway, James A. Allison had built something entirely different. The Allison Experimental Company was not a mass production factory. It was a precision machine shop, a place where mechanics and master machinists turned raw steel into specialized gears, supercharger parts, and racing components. When Jim Allison died in 1928, his shop was a boutique operation, highly respected for its exactness, but incredibly small in scale. A year later, in 1929, General Motors purchased the company. The massive automotive corporation did not buy Allison to conquer the aviation world. They bought it because they needed a high-quality machine shop to support their own research and development. They inherited a workforce that inherently understood precision tolerances, the kind of mechanical perfection required for high-speed bearings and complex gearing. At the exact same time, the United States Army Air Corps was facing a severe mechanical crisis. Across the Atlantic, European nations were developing sleek, aerodynamically clean fighter planes powered by liquid-cooled V-12 engines. America, however, was a radial engine country. A radial engine, a piston aircraft engine with cylinders arranged in a circle around the crankshaft, did not only power airplanes, it gave American aviation its foundational reliability. Engines from Pratt & Whitney and Wright Aeronautical were air-cooled, meaning they relied on the slipstream of air flowing over their exposed cylinders to keep them from melting down. They were rugged, durable, and relatively easy for mechanics to service on the ramp or inside a drafty hangar. But that massive frontal area created immense aerodynamic drag. If the military wanted to push fighter aircraft speeds past 300 miles per hour, they needed an engine that could be hidden inside a narrow, pointed nose. They needed a liquid-cooled V-12, a liquid-cooled engine, an engine design that pumps a coolant mixture through channels in the engine block and cylinder heads to carry away heat, allowed aircraft designers to build a much narrower, streamlined shape. General Motors, realizing the opportunity in the military's desperation, directed the small Indianapolis shop to develop a massive V-12 engine. The project was designated the V-1710. The name was not a marketing term. It was a pure physical measurement. The engine displaced exactly 110 cubic inches across 12 cylinders, arranged in a 60-degree V-shape. Designing the engine on paper was one problem. Forcing it to survive the brutal realities of aviation was another. In the early 1930s, the Great Depression had hollowed out much of American manufacturing. Foundries sat idle, and skilled labor was desperate for work. Yet inside the Allison plant, the pressure was relentless. They were not building a heavy, low-stress tractor engine. They were attempting to master high-compression combustion on 100-octane aviation fuel. The Allison engineers cast the engine blocks from lightweight aluminum alloy, a material that saved critical weight but was incredibly difficult to cast perfectly without internal flaws. Inside those blocks, they fitted overhead camshafts, a design where the camshaft located above the combustion chambers directly actuates the valves, allowing for higher RPMs and better breathing than traditional pushrod designs. Every component was a metallurgical puzzle. The cylinder head, the upper part of the engine that helps seal the cylinders and contains the intake and exhaust valves, had to withstand brutal heat cycles without warping. The engine used a liquid cooling system pressurized with ethylene glycol, known by the trade name Piston, allowing it to run at much higher temperatures than pure water. The crankshaft, the massive rotating steel shaft that turns the violent up and down motion of the pistons into the rotational power needed to spin a propeller, had to be machined to tolerances of 10,000ths of an inch. If it flexed even slightly under the immense torque, the engine would tear itself apart. The Army Air Corps demanded absolute reliability before they would commit to fleet orders. Their standard was a grueling, continuous 150-hour type test. The engine had to run on a test stand at varying power settings without catastrophic failure, structural cracking, or excessive oil consumption. For years, the V-1710 struggled. The early prototypes suffered from cracked cylinder heads, bearing failures, and coolant leaks. In an American machine shop, a mechanic can pull a truck over and replace a blown head gasket. In an aircraft engine, a coolant leak at 15,000 feet is a fatal event. The engineers at Indianapolis tore down the failed blocks, analyzed the broken connecting rods, the heavy steel parts that link the piston to the crankshaft, and redesigned the bearing shells. By April 1937, the Allison V-1710 returned to the test stand. For 150 hours, it ran on high-octane aviation gasoline, turning its massive crankshaft with a smooth, continuous roar that echoed through the Indianapolis testing facility. When the test concluded, the engineers tore the engine down for inspection. The bearings were intact. The aluminum block held. It became the first aviation engine in American history to pass the 150-hour test with a verified rating of 1,000 horsepower. That 1,000 horsepower rating changed everything. It proved that an American manufacturer could match the elite European V12s. But a prototype on a test stand is not a service network. It is not a fleet. In 1937, the Allison factory in Indianapolis was still essentially a boutique machine shop. They had built the engine by hand, machining the parts with agonizing care. The military did not need a handful of engineering masterpieces. With the threat of a global war looming, they needed thousands of them, identical, reliable, and backed by a global supply chain of replacement parts, service manuals, and trained mechanics. They needed an engine that could be shipped in a wooden crate to an airfield in a remote part of the world and trusted to start on the first crank. The engineering challenge was over. The industrial challenge was just beginning. General Motors now had to figure out how to take the precision of a master machinist and replicate it on an assembly line. The block was ready. America still had to decide how to build it by the thousands. General Motors knew how to build Chevrolets by the millions, but mass-producing an aviation masterpiece required an entirely different industrial language. The breakthrough of the Allison V-1710 was not merely its design, it was the translation of that design into a repeatable, high-volume process. Before 1939, the Allison plant in Indianapolis operated like a traditional machine shop. Highly skilled artisans crafted individual parts, hand-fitting components together. If a gear did not mesh perfectly, a machinist would file it down until it did. But the United States Army Air Corps did not have time for hand-fitted artistry. As war escalated in Europe, the military demanded production rates that seemed impossible for a liquid-cooled V-12. General Motors responded by building Plant 3 in Indianapolis, the first windowless, fully air-conditioned manufacturing facility in America, designed specifically to prevent temperature shifts from altering the microscopic tolerances of engine parts during machining. The immediate mechanical advantage of the V-1710 was its shape. A massive air-cooled radial engine had a wide, blunt profile that pushed through the air like a brick. The Allison, with its 12 cylinders arranged in a tight 60-degree V, was astonishingly narrow. This allowed aircraft designers at Lockheed to draw up the P-38 Lightning, a radical twin-engine interceptor where the powerful Allisons were tucked inside sleek, aerodynamic booms. At the Curtiss-Wright plant in Buffalo, New York, Engineers used the narrow Allison to design the sharp, pointed nose of the P-40 Warhawk, an aircraft that would soon become famous wearing painted shark teeth. But making that aerodynamic shape work meant solving complex internal forces. The engine spun fast, far faster than a propeller could efficiently turn. To fix this, Allison engineered a heavy-duty reduction gear. A reduction gear, a mechanical gear set mounted at the front of the engine that slows the spinning of the propeller relative to the engine's crankshaft, was critical. If a propeller spun at the engine's 3,000 RPM redline, the tips of the blades would break the sound barrier, creating deafening noise, destructive vibration, and a massive loss of thrust. The Allison reduction gear allowed the engine to scream at high RPM, while the propeller bit into the air at a steady, efficient pace. In an American hangar, the reduction gear was not just an engineering concept. It was a distinct, high-pitched mechanical whine that pilots and ground crews learned to recognize long before the plane came into view. The real triumph of the Indianapolis factory floor was standardization. General Motors broke the complex assembly of a 1,000 horsepower V12 down into smaller, manageable steps. They brought in specialized milling machines that could cut exact profiles automatically. They trained thousands of new workers, many of them women entering the heavy industrial workforce for the first time, to operate precision grinders and lathes. The goal was absolute interchangeability. A cylinder block machined on a Tuesday morning in Indiana had to bolt perfectly onto a crankcase machined on a Thursday night. And later, out in the field, a mechanic had to be able to swap a damaged part with a replacement from a wooden crate without having to hand file the metal to make it fit. By 1941, the V-1710 was no longer a boutique experiment. It was the only American-built, liquid-cooled engine ready for combat. To make power, an engine needs air. At sea level, the atmosphere is dense, and the engine breathes easily. But fighter planes needed to fight at 15,000 or 20,000 feet, where the air is thin. To solve this, the engine required a supercharger. A supercharger, a mechanically driven air compressor powered directly by the engine's crankshaft, forces a dense mixture of air and fuel into the cylinders, allowing the engine to maintain sea-level power high in the atmosphere. Allison engineers designed the V-1710 with an excellent, highly reliable single-stage supercharger. It was driven by a complex set of gears at the back of the engine, whining with immense mechanical force as it packed air into the intake manifolds. But the supercharger also represented a fateful decision by the military bureaucracy. The Army Air Corps believed that the future of high-altitude flight relied on exhaust-driven turbochargers, a different technology entirely. They instructed Allison to keep the mechanical supercharger simple, optimizing the engine for low and medium altitudes, while the military would bolt massive, heavy turbocharger systems onto the airframes later if they needed to go higher. On a plane like the Lockheed P-38 Lightning, which had the space to carry those massive external turbos, the Allison engines performed flawlessly at 30,000 feet. But on smaller single-engine fighters like the Curtiss P-40 Warhawk, there was no room for the extra plumbing. At the time, this did not seem like a fatal flaw. The breakthrough was scale, reliability, and speed of delivery. Out on the flight lines, mechanics uncrating a new Allison V-1710 found a machine that felt distinctly like an American automotive product, just scaled up to a terrifying degree. It used an electric starter rather than the dangerous hand-cranked inertia starters of the past. Its ignition system, the magnetos and wiring that deliver electrical spark to the cylinders, was shielded and robust. It did not leak oil the way older radials did. It ran on a pressurized system of Prestone liquid coolant, giving off a distinct, sweet chemical smell when the engine ran hot. General Motors had done exactly what the country asked. They had taken a jewel of a race shop and turned it into an industrial sledgehammer. Production skyrocketed from dozens a month to hundreds, and soon to over 1,000 engines every 30 days. The engine had found its airframes and its assembly lines. But out on the flight lines, the American military was about to test the limits of what a mass-produced machine could actually survive. By 1943, the sky over Indianapolis sounded like a continuous, rolling thunderstorm. General Motors had pushed Plant 3 into a state of permanent, deafening motion. The Allison Experimental Company was no longer a boutique race shop where men hand-filed gears. It was an industrial leviathan. At its absolute peak, the assembly lines were churning out nearly 1,000 liquid-cooled V12 engines a month, a staggering rate of heavy manufacturing that would eventually push the total production run past 70,000 units. This was the emotional and physical peak of American piston aviation. The engine was no longer just an engineering drawing or a prototype on a test stand. It had become a sprawling, global system of power. Inside the Indianapolis facility, the air was thick with the smell of cutting oil and hot metal. The floors vibrated with the rhythmic stamping of heavy presses and the high-pitched whine of milling machines. Thousands of workers, many of them women who had never touched a micrometer before the war, were machining aluminum engine blocks, steel crankshafts, and delicate supercharger impellers to tolerances of a 10,000th of an inch. They were not just building parts, they were building absolute mechanical certainty. When a cylinder head was bolted onto a block, it sealed perfectly. When a reduction gear was fitted to the front case, it meshed flawlessly. General Motors had taken the delicate, temperamental nature of a high-performance V12 and forced it into the rigid, repeatable discipline of an automotive assembly line. That discipline translated directly into survival for the mechanics working thousands of miles away. In the dirt and mud of forward operating bases in the Pacific or on the dusty airfields of North Africa, a mechanic did not have the luxury of a clean room. When a fighter plane limped back with a blown cylinder or a shattered gear case, the ground crew had to swap the engine quickly. Because of the obsessive standardization at the Indianapolis plant, a mechanic could tear open a wooden shipping crate, hoist out a brand new 1,500-pound Allison V-1710, and know that every bolt hole, every coolant line, and every throttle linkage would line up exactly with the airframe. The service manuals, often stained with oil and dirt, became the Bibles of the flight line. The Allison V12 was not just powerful, it was incredibly durable. It could take battle damage, overheat, and still drag a heavy fighter back to base. This ruggedness made it the beating heart of two of the most famous aircraft in American history. In the skies over China, the Curtiss P-40 Warhawks of the Flying Tigers relied entirely on the Allison V-1710. The P-40 was a heavy fighter, not particularly nimble, but the Allison engine gave it excellent low-altitude speed and a devastating diving capability. The pilots learned to trust the smooth, continuous roar of the V-12. In the Pacific Theater, the Lockheed P-38 Lightning used two Allison engines tucked inside its twin booms. The P-38 was a massive interceptor, but with two V-1710s spinning in opposite directions to cancel out the massive torque, the twisting force that would otherwise violently roll the aircraft on takeoff, the Lightning became a devastatingly fast, long-range weapon. In an America where an engine could decide whether a plane held the high ground or fell from the sky, power was not an abstraction. It was iron, fuel, supercharger pressure, and the trust of the pilot in the cockpit. For a brief, shining moment, the Allison V12 was the undisputed king of the American liquid-cooled sky. It had achieved the impossible, matching European refinement with Midwestern mass production scale. The factory was running at maximum capacity. The dealer network of military supply chains was pushing parts to every corner of the globe. The engine was trusted by fleet commanders and individual pilots alike. But aviation is a ruthless environment. An engine on a tractor or a truck only has to fight gravity and rolling resistance. An aircraft engine has to fight the atmosphere itself. The Allison was structurally bulletproof. The block was perfect. The assembly line was a marvel of the world. But deep inside the military bureaucracy, a decision had already been made about how this engine was allowed to breathe. A decision that was about to expose a fatal flaw in the system. The engine was a masterpiece of mass production. The market, however, was about to demand a different kind of power. By late 1944, the Allison V-1710 was no longer just an engine. It was a unit of American industrial currency. If you stood in the massive rail yards outside of Indianapolis, you would not just see trains. You would see the sheer, overwhelming scale of General Motors' manufacturing dominance. Boxcar after boxcar was loaded with heavily reinforced wooden crates, each stenciled with military serial numbers and packing dates. Inside each crate was a 1/500 horsepower, liquid-cooled V12, heavily coated in a rust-preventative compound, ready to be shipped across the globe. The peak of the Allison empire was defined by its absolute adaptability. The engine was so reliable, so perfectly standardized, that aircraft designers began using it in ways Jim Allison could never have imagined. At the Bell Aircraft plant in Buffalo, New York, engineers designed the P-39 Airacobra, a radically unconventional fighter, where the heavy Allison V12 was not mounted in the nose, but placed dead center in the fuselage, directly behind the pilot. To make this work, the engine's power had to travel through a 10-foot steel drive shaft that ran right between the pilot's legs, connecting to a separate reduction gearbox in the nose to spin the propeller. If the engine vibrated excessively, or if the block flexed under load, that drive shaft would have torn the aircraft apart in midair. But the Allison block, cast in perfect aluminum, machined to exact tolerances, did not flex. It ran with a smooth harmonic balance that allowed the Airacobra, and later the P-63 King Cobra, to become devastating low-altitude weapons, particularly when shipped by the thousands to the Soviet Air Force through the American Lend-Lease program. Behind every one of those engines was an invisible, globe-spanning service network. A service network, the dealers, mechanics, parts suppliers, and manuals that keep a machine running after purchase, in wartime meant the difference between a grounded fleet and air superiority. General Motors did not just build the engine. They built the entire culture of maintenance around it. They produced beautifully illustrated, highly detailed service manuals that could teach a farm boy from Iowa how to adjust the valve lash on a dual overhead cam V12, using only the tools provided in a standard military kit. The parts supply was so deep that mechanics stationed on remote dirt runway islands in the Pacific rarely had to wait for critical components. If a cylinder head cracked from battle damage or overheating, there was a replacement waiting in a supply tent. The engine was designed so intuitively that ground crews could strip an Allison down, swap out damaged components, and have the aircraft running again before the next morning's patrol. In Indianapolis, the workforce had settled into a relentless, deafening rhythm. The test cells, heavily reinforced concrete rooms where newly assembled engines were run up to maximum power before shipping, roared 24 hours a day. The sound of a V12 running at 3,000 RPM on 100-octane aviation fuel is a distinct, visceral scream. It is a dense mechanical noise driven by the furious meshing of the supercharger gears and the explosive bark of 12 cylinders firing in rapid succession. For the people living near Plant 3, that continuous rolling thunder was the sound of American security. General Motors had achieved total mastery over liquid-cooled piston power. They had scaled production past 50,000 units, then 60,000, ultimately heading toward an astounding total of over 70,000 V-1710 engines. They had crushed the manufacturing bottlenecks. They had solved the metallurgical flaws. They had proven that American mass production could build a precision machine as well as the finest European craftsmen, and build it thousands of times faster. The badge on the engine meant durability. The factory behind it was running at peak efficiency. The pilots who flew low-altitude attack missions trusted it with their lives. But aviation is a game of altitude, and altitude is a game of breathing. The Allison V-1710 was a mechanical masterpiece, but it was trapped by the military's rigid doctrine. The Army Air Corps had commanded General Motors to build a simple, single-stage supercharger, insisting that heavy external turbochargers would handle the high-altitude work. On the massive twin-engine P-38 Lightning, that system worked. But on smaller single-engine fighters, there was no room for the extra plumbing. As the air war over Europe shifted higher and higher, the limits of that decision began to show. At 10,000 feet, the Allison was a monster. At 15,000 feet, it was competitive. But at 25,000 feet, in the thin, freezing air, where the bomber formations flew, the engine began to starve for oxygen. The engine was perfect for the war it was designed to fight. The market, however, was moving higher. The crack in the empire would not start on the factory floor in Indiana. It would start on a drafting table with a completely different engine, designed by the British and built by a rival American automaker. The first crack in the Allison empire was not a mechanical failure on the factory floor. It began as a slow, quiet realization in the freezing, thin air over Europe. In 1940, a company called North American Aviation designed a revolutionary new fighter aircraft in just 102 days. It was called the P-51 Mustang. To power it, they chose the Allison V-1710. When the British Royal Air Force tested the early Allison-powered Mustangs, they found them to be magnificent machines at low altitudes. Below 15,000 feet, the plane was fast, agile, and aerodynamically perfect. But the air war over Europe was not being fought near the ground. It was being fought at 25,000 and 30,000 feet, where the heavy bomber formations flew. At that altitude, the air is incredibly thin. The Allison V-12, restricted by the American military doctrine that mandated a simple single-stage supercharger, began to suffocate. The engine was perfectly built, but it simply could not pack enough oxygen into its cylinders. As the plane climbed higher, the horsepower dropped dramatically. The Mustang became sluggish, vulnerable, and completely unsuited for the high-altitude escort missions the Allies desperately needed. The problem was not the engine block. The problem was the rule book that had dictated its design. That strength, the simplicity and ruggedness of the single-stage supercharger, had become a fatal trap. To solve the problem, British engineers proposed a radical swap. They took the airframe of the American P-51 and bolted in a British-designed Rolls-Royce Merlin engine, which was being mass-produced in America by the Packard Motor Car Company. The Packard Merlin featured a two-stage supercharger, a mechanical compressor system that forces air through two separate high-speed impeller wheels in sequence, multiplying the air pressure enough to feed a massive V-12 even in the freezing, thin atmosphere of 30,000 feet. When the two-stage Merlin was mated to the aerodynamic perfection of the Mustang, it created a devastating high-altitude weapon. The P-51 went on to become the definitive American fighter of the war, escorting heavy bombers all the way to Berlin and back. But it did so without the Allison engine. This was a profound systemic shift. General Motors was still building thousands of V-1710s at the Indianapolis plant. The engine had not stopped working, but it had lost the prestige of the high-altitude war. The Allison was relegated to low and medium-altitude duties. It powered the P-38 Lightnings in the Pacific, where the planes carried their own massive external turbochargers. It powered the heavy P-40 Warhawks. It powered thousands of P-39 Airacobras shipped to the Soviet Union, where the air war was fought at lower altitudes over the freezing mud of the Eastern Front. The engine was still a workhorse, but a psychological line had been crossed. The Allison V-12 was no longer seen as the absolute pinnacle of aviation performance. It was a rugged, reliable tool, a mass-produced piece of iron and aluminum that did the dirty, low-level work, while the Packard Merlin claimed the glory of the stratosphere. In Indianapolis, the factory lines did not slow down. Plant 3 was still a deafening cathedral of American manufacturing, churning out engines by the thousands. The dealer network of military logistics was still shipping spare parts, cylinder heads, and gaskets to every corner of the globe. Mechanics in the field still praised the engine for its durability, its easy electric starting, and its ability to absorb battle damage and keep running. If a cylinder bank took a bullet, the mechanic knew they could swap it out with a replacement from a wooden crate and trust the tolerances to be perfect. But as 1944 turned into 1945, the mechanical landscape began to shift again. The war was ending, and the massive military contracts that sustained the Allison Empire were about to evaporate. General Motors had scaled its production to build nearly 1,000 V-12s a month. They had built an industrial machine designed for a level of consumption that peacetime could never support. Even worse, the rules of aviation were changing faster than a piston engine could adapt. Engineers were no longer looking for ways to squeeze more power out of a 1/10 cubic inch block. They were looking at an entirely new way to burn fuel. The Allison V-12 had survived the grueling 150-hour test. It had survived the demands of mass production. It had survived the high-altitude limits imposed by military doctrine, and it had survived the rivalry of the Packard Merlin. The machine was running perfectly, but the next rival did not have pistons, valves, or a crankshaft at all. In the summer of 1945, the deafening roar of Plant 3 in Indianapolis finally began to quiet down. The war was over. Almost overnight, the United States government canceled millions of dollars in defense contracts. General Motors had built an industrial machine capable of producing nearly 1,000 V-12 engines every month, and suddenly the single massive customer that sustained that empire stopped calling. But the death of the Allison V-1710 was not just a matter of peace, it was a matter of physics. Even before the final piston engines rolled off the Indianapolis assembly line, the sky had already been claimed by a completely different kind of power. The jet engine, a turbine engine that produces thrust by accelerating air and exhaust gases, did not need massive steel crankshafts, complex reduction gears, or high-octane aviation gasoline carefully mixed by a carburetor. It swallowed air, compressed it with spinning turbine blades, ignited it with kerosene, and blasted it out the exhaust nozzle. In a military hangar, a mechanic who had spent years mastering the intricate valve lash of a dual overhead cam V12 was suddenly staring at a smooth cylindrical tube that produced twice the speed of a P-38 Lightning with a fraction of the moving parts. The deep mechanical trust that Allison had built over a decade of trial and error was instantly rendered obsolete. You cannot adjust the valves on a jet engine because there are no valves. You cannot time the ignition magnetos because the fire never stops burning. The military looked at the new jet-powered P-80 Shooting Star and realized that the era of the liquid-cooled piston fighter was over. The V-1710 went from being the absolute vanguard of American defense to a piece of legacy equipment in a matter of months. General Motors, as a corporation, did not collapse. The military still needed engines, and the Allison division was still a master of mass production. The government simply handed Allison the production rights to the new J3 turbojet, an engine originally developed by General Electric, because GM had the factory floor space and the workforce to build it at scale. The workers at the Indianapolis plant simply retooled their machines. The factory survived. The brand name survived, eventually pivoting toward heavy-duty truck transmissions and turbine engines. But the V12 engine line was shut down forever. What happened next was one of the most brutal and sudden devaluations of mechanical engineering in American history. By the end of 1945, the military owned tens of thousands of unused Allison V-1710s. They were sitting in stateside warehouses, stacked in shipyards, and waiting in forward supply bases. They were no longer vital assets. They were thousands of pounds of surplus metal taking up valuable space. The government ordered a massive sell-off. Across America, in the back pages of local newspapers and trade magazines, strange advertisements began to appear. A liquid-cooled, 1,500 horsepower aviation masterpiece, packed in a hermetically sealed, heavy-duty wooden shipping crate alongside its original factory service manual, was offered to the American public. The price was a shock. An engine that had cost the government tens of thousands of dollars in research, development, and high-precision manufacturing was sold for as little as $50 or $100. For the aviation industry, the engine was a dinosaur. But for the American public, it was cheap, heavy iron. Mechanics, hot rodders, and scrap dealers bought the crates by the dozens. At farm auctions in the rural Midwest, a farmer might buy a crated Allison just to get the heavy-duty wooden box for storing tools, leaving the massive aluminum V12 sitting out in the weather. Scrap metal yards bought them simply to melt down the high-quality aluminum engine blocks. Mechanics bought them just to rip off the shielded ignition wires, the heavy-duty electric starters, or the industrial-grade spark plugs, tossing the rest of the engine into the weeds. The massive parts network collapsed. The beautifully illustrated service manuals, once treated like Bibles on the flight line, were tossed into dumpsters or left to rot on the shelves of closed military bases. The supply chain of gaskets, pistons, and supercharger gears lost all commercial value. General Motors had built over 70,000 of these engines. They were designed to dominate the sky, engineered to tolerate the brutal forces of aerial combat, and manufactured with a level of precision that rivaled watchmaking. But the market did not care about precision once the technology shifted. The engine was heavy. It was complex. It burned massive amounts of fuel. And without an airplane to pull, it was completely useless to the average American. The V-1710 was pushed into the dark corners of the American landscape. They were shoved into the backs of barns, buried under tarps and salvage yards, and left to sink into the mud of surplus lots. The engine still ran. The military stopped buying. The rulebook changed. The jet took the sky. The factory line retooled. The crates were sold for scrap. The badge survived on a different machine. The world it was built for was gone. General Motors did not let the Allison name die. The corporation had too much engineering talent and too much highly specialized factory space in Indianapolis to simply board up the windows. The plant abruptly stopped building piston aircraft engines and pivoted immediately into the new era, building the early J-33 turbojet engines that would power America's first generation of jet fighters. Decades later, the Allison division would pivot again, eventually becoming a global powerhouse in heavy-duty commercial transmissions. Today, if you look under a city bus, a highway dump truck, or a heavy piece of construction equipment, you will likely see the Allison badge cast into the side of the gearbox. The name survived. The business model adapted to the modern world. But the deep, mechanical V12 sound that once shook the factory floors in Indiana was gone forever. The aviation industry had moved on to the high-pitched scream of turbines and the clean logic of jet propulsion. Yet the story of the Allison V-1710 did not end when the military canceled the contracts. Because the United States government had sold off tens of thousands of these masterpiece engines for pennies on the dollar, the V-12 found a completely new, unauthorized afterlife in the hands of American hot rodders, mechanics, and independent racers. The engine was far too heavy for a standard street car, but it was perfect for anyone who needed raw, catastrophic horsepower and did not care about altitude limitations. In the late 1940s and throughout the 1950s, on lakes across America, the Allison V12 gave birth to the golden age of unlimited hydroplane racing. Boat builders bought crated V-1710s, stripped away the heavy military reduction gears, bolted them into lightweight wooden hulls, and created a legendary class of racing boats known as thunderboats. On the waters of Detroit, Michigan, and Lake Washington and Seattle, these surplus war machines roared across the waves at over 160 miles per hour, throwing massive rooster tails of water into the air. The engine that was designed to shoot down enemy fighters was now fighting for trophies on American weekends, maintained by mechanics who bought spare parts from surplus catalogs instead of military supply depots. But the Allison found its most violent, visceral home deep in the American Midwest. In the rural farming communities, a new mechanical sport was taking over the county fairs: tractor pulling. It was a simple concept. A machine had to pull a heavy drag-inducing weight transfer sled down a dirt track. Standard farm tractors eventually gave way to custom-built monsters. Mechanics who had learned to wrench on Allisons during the war realized that a 1,500 horsepower V12, which cost almost nothing to buy and could absorb incredible amounts of abuse, was the ultimate pulling engine. Soon the dirt tracks of Ohio, Illinois, and Indiana were shaking with the sound of aircraft engines. Builders bolted 2, 3, or even 4 Allison V-1710s to a single tubular steel frame, linking their massive crankshafts together in a terrifying display of unregulated mechanical power. When those engines fired, they burned alcohol and aviation fuel, spitting raw fire from straight pipe exhausts. They dragged heavy steel sleds through the mud with a sound so deafening it rattled the wooden bleachers and echoed across the cornfields. This is not nostalgia. A surviving Allison V-1710 sitting on a reinforced engine stand or bolted to a tractor-pulling chassis is a physical argument about the peak of American industrial hubris. It proves that there was a brief, intense window in history when an automaker like General Motors could take the delicate, temperamental design of a liquid-cooled V12 and mass-produce it with such brutal perfection that the engine outlived its original purpose by decades. It represents a time when horsepower was measured not by software, electronic fuel injection, or hybrid battery assist, but by physical displacement, mechanical supercharger gears, and the deafening rush of air and fuel forced into 12 massive cylinders. The engineers who designed it and the thousands of women who machined its perfect gears in windowless factories built a machine so fundamentally strong that even when the sky no longer wanted it, the earth still could not break it. Today, the pristine examples of the Allison V-1710 are sitting under soft lights in aviation museums, perfectly preserved, static, and silent. They are displayed as artifacts of a war that was won a lifetime ago. But the true soul of the Allison V12 is not found in a quiet museum case. Somewhere in the rural Midwest, an old Allison V-1710 still sits strapped to a heavy steel tractor frame inside a corrugated machine shed, its massive aluminum block stained with oil. The supercharger housing caked in dried track mud, waiting to be fired up to unleash a sound that the sky left behind long ago. See you in the next video.